Okay, I've got a furnace, and what I have is 75-degree air coming in at 800 cubic feet per minute, and then the furnace delivers the air at 120 degrees down 3 different ducts. 2 ducts have a 6-inch diameter, and the speed is at 10 feet per second, and the third duct has a diameter of 12 inches. Okay, and all of this, all the pressures are 1 atmosphere. Okay, so I want to find the mass flow rate of the inlet. I want to find the volumetric flow of the 6-inch ducts, and then I want to find the velocity in the 12-inch duct. Okay, so I'll start with the mass flow rate of what's coming in. So again, our definition for mass flow rate of the inlet is going to be the volumetric flow, AV, all over the specific volume of the inlet. Now, again, don't confuse velocity with specific volume. Okay, air is an ideal gas, so instead of specific volume, what I'll use instead is RT over P, right? Because PV equals RT. So I get P A V, again, that's volumetric flow rate, divided by RT, and this is for the inlet. So the pressure coming in is 1 atmosphere, okay, which is 14.7 psi, which I take times 144 to get in pounds per square foot. Okay, so I get everything in pounds and feet. Okay, and I multiply that times 800 cubic feet per second. I'm sorry, cubic feet per minute. So I need to divide that by 60 seconds to get that in cubic feet per second. So now I've got everything in pounds, feet, and seconds on the top. On the bottom, I have R. Now I want everything in feet and pounds, so I'll use the foot-pounds version, which is going to be 1545 divided by the molecular weight of air, which is 28.97. Again, that takes it from pounds mole to just pounds, okay, times the temperature, which is 75 degrees Fahrenheit, which I need to convert to Rankine. So that is all of the unit conversions. Plugging in all of those numbers, I'm going to get, and now remember, everything's feet, pounds, seconds, so I'm going to have pounds per second as my answer. And the mass flow coming in is 0.989 pounds per second. Okay, so that is the mass flow coming in. The next thing we need to find is the volumetric flow rate coming out of these guys here. Okay, so the volumetric flow rate is the area times the velocity. The velocity is given 10 feet per second, so all I really need to do is find the area. Now the area of a circle is pi over 4 times the diameter squared, again, times that velocity. Now I'm going to get everything in feet, and I ultimately want to get it into minutes, so we have to convert feet per second to feet per minute. But plugging in my values, I get pi over 4. My diameter, rather than 6, is going to be 1/2, but I'll just do 6/12 to get that into feet from inches. And then 10 feet per second times 60 to get it in feet per minute. And I find that the volumetric flow rate of this guy is 117.8. 117.8, and that is cubic feet per minute, or what we would call CFM. Okay, now I want to find what's going on duct 3. Okay, so what I'm going to do is I'm going to set up my conservation of mass equation. So now that I have my volumetric flow rate, what I'm going to do is I'm going to calculate this mass flow. This would be mass flow, 1 and 2. Right? I'm calling those ducts 1 and 2, which again, just like before, is going to be PAV over RT. Okay, and in order to save time, we've got this all here, right? The only real difference here is instead of 800, I'm going to use 117.8, and instead of 75, I'm going to use 120. Other than that, all the conversions and the pressure and things are the same, and I find that that equals 0.1343. That would be pounds per second. Okay. From this, I'm going to use my conservation of mass equation, which is essentially mass flow in equals mass flow out, which basically means my mass flow in equals mass flow 1 plus mass flow 2 plus mass flow 3, which is, again, 0.989 equals 2 times plus mass flow 3. So again, I've got two of these with that sort of a mass flow. This is what's coming in. Therefore, the mass flow in duct 3 is actually 0.7204 pounds per second. Now that I have that, in order to find the velocity, I use this same equation, right? Where the mass flow of 3 equals, P A V3 all over RT. Again, same ideas here. Okay, temperature of 120, right? The only difference is now I have a mass flow. I'm solving for V3, but using those same unit conversions, plugging in 120 for this guy, plugging in 0.720 for this guy. The area is 1 foot in diameter. I can calculate that velocity to be 13.4 feet per second. So again, the main two things here are, this is our relationship for mass flow to volumetric flow, and then my conservation of mass principle, where the mass flow in has to equal the mass flow out, helps us determine the different flows in each of the ducts.